Hello dear students, I hope you're fine. Remember to put on your mask, to sanitize and practice social distancing. So since I'm alone in this room, I can remove my mask and go ahead with our presentation. We are going to look at linear motion. What is linear motion? Linear motion is the movement of a body in one dimension from one place to another in a straight line. It may involve a person moving, running, or even when he's seated in one place. Linear motion may be carried out when one person moves from one place to another. When a car is moving from one place to another, also carries out linear motion. We have some important terms in linear motion. We have distance is a space between 2 points. We have displacement, which is a distance moved in a specified direction. Both distance and displacement have the same SI unit, which is meters. Though distance is a scalar quantity, while displacement is a vector quantity. We have another term, which is speed, is a rate of change of distance, or is a distance moved in the unit time. Its formula is given by distance is equal to speed is equal to distance over time, while velocity may be defined as a rate of change of displacement or speed in a specified direction. Velocity is given by formula displacement over time. Both speed and velocity have the same SI unit, which is meters per second. Though speed differs from velocity, being that speed is a scalar quantity while velocity is a vector quantity. Here are some of the differences between speed and velocity. Velocity is a vector quantity while speed is a scalar quantity. Displacement over time is a formula for velocity, while speed is equal to distance over time taken. We have some different types of velocities, which include initial velocity. U is the velocity with which the body starts motion in a given time interval. When the body is at rest, it has an initial velocity which is 0 meters per second. Also, a stationary body has an initial velocity of 0 meters per second. When you have a moving body, for example, a car, the velocity with which it moves with is called initial velocity. Like that example you're seeing below, a car is traveling at 20 meters per second. This implies that its initial velocity is 20 meters per second. We have uniform velocity. Is the constant rate of change of displacement, or uniform velocity is when the body makes an equal displacement in equal time intervals. When a body moves with uniform velocity, its initial velocity must be equal to the final velocity, i.e. V is equal to U. We have an example there. A car traveling with a uniform velocity of 20 meters per second. It has an initial velocity of 20 meters per second and a final velocity V of 20 meters per second. When a body moves with a uniform velocity, its acceleration is always equal to 0. So we have another term here for acceleration, and we normally use the symbol A, small a, to represent acceleration. Acceleration is a rate of change of velocity with time, and it's given by a formula that change in velocity over time taken. So its SI unit for the acceleration is meters per second squared. We have a definition there for uniform acceleration, which is the rate of change of velocity with time, or uniform acceleration is when a body moves with equal change in velocity with equal time intervals. Now, we have an example there. A car starts from rest and it accelerates at 10 meters per second. Calculate the change in velocity. Remember, we said that when a car starts from rest, its initial velocity is always 0. That's why we are representing u equal to 0, while the final velocity will go to 20 meters per second. So the difference will be the change in velocity, which is v minus u. So we shall have 20 meters per second minus 0. So our final answer will be 20 meters per second. So we have another type of velocity which is called final velocity. The velocity with which a body ends motion for a given time is what we call final velocity. And we normally use symbol capital V to represent final velocity. Now, if you have an example, for example there, that a body traveling at 20 meters per second is uniformly brought to rest in 2 meters per second, this implies that the final velocity will be 0 because the body was brought to rest. And remember, we said that when a body comes to rest, its velocity, whether initial or final, the velocity will always be 0. We have another formula there for average velocity. From the previous type, we learned that the final velocity plus initial velocity, which we normally use u over 2, will represent average velocity. So if you add final velocity plus initial velocity, divide by 2, you'll be able to get the average velocity. Now, we're going to look at the equations of motion. We normally have 3 equations of motion. We shall look at one at a time. So, this first slide is going to talk about the first equation of motion. We derive our first equation of motion from the formula that acceleration is equal to change in velocity over time taken. Remember, we said small a represents acceleration, small t represents time, small v represents final velocity, and small u represents initial velocity. So if we make v the subject of the formula, we shall have v is equal to u plus at, which represents the first equation of motion. We have the second equation of motion, which we derive from displacement. Displacement, we can use small s or small x to represent the length moved in a specified direction. From the definition of displacement, which is average velocity times time, remember we say that average velocity is equal to v plus u over 2 times time, which is small t. So we shall apply the first equation and we substitute for v, which is equal to v is equal to u plus at. We shall substitute where we see v, we will substitute the first equation and we try to simplify the expression. So if we multiply t, small t, which was outside, multiply it inside the formula, we shall be able to make or try to simplify the expression and have t multiplied both terms, where we shall have s is equal to ut plus a half at squared. That represents the second equation of motion. The last equation of motion is what we call the third equation of linear motion, and we derive that from the formula displacement is equal to average velocity times time taken. So from the previous formula, we make t the subject of the first equation of linear motion, and we substitute it here, and we'll be able to get s is equal to u plus t, u plus v, small v plus u over t times v minus u over a. We multiply the denominators together and multiply also the numerators together. Since you look at the numerators, it's a difference of two squares. We shall end up by cross multiplying and have 2as is equal to v squared minus u squared. If we make v squared the subject, this implies we have to take u the other side. We shall be able to obtain v squared is equal to u squared plus 2as, which gives us the third equation of linear motion. So we are able to organize some worked up examples which you can follow. We have example 1. A body starts from rest, is accelerated to 30 meters per second in 2 seconds. Calculate the acceleration of the body. So from the question we are given that the initial velocity is 0, why the body was at rest, the final velocity is 30 meters per second, while the time it took to go to 30 meters per second was 2 seconds. So judging from what we are having from the question, we shall be able to use the first equation of linear motion, which is v is equal to u plus at, and we shall substitute in the final velocity, which is 30. Our initial velocity is 0 and the time taken was 2, and we shall try to simplify using the mathematical concepts and divide both sides by 2, giving us the acceleration of a body as 15 meters per second squared. When you look at example 2, a body starts from rest and accelerates uniformly at 2 meters per second squared for 3 seconds. Calculate the final velocity. Now from the question, we don't have the final velocity. Though the question provided us with the initial velocity, which is 0 meters per second, it has an acceleration of 2 meters per second squared and time of 3 seconds. So if still we use the first equation of linear motion, we shall substitute in the initial velocity, which is 0, acceleration, which is 2, and time, which is 3. And since initial was 0, we shall only multiply the acceleration times time, which gives us 6 meters per second squared. And that will represent the final velocity of the body. We have example 3. A body moving at 40 meters per second decelerates uniformly for 20 seconds at 3 meters per second squared. Calculate the time, calculate the distance covered. Now, we have a term there, deceleration. Normally, when a body is coming to rest, it decelerates. And since it is decelerating, it will be moving with a negative acceleration. We are given initial speed of 40 meters per second, an acceleration of negative 3 meters per second squared because the body was decelerating, and time it took to decelerate was 20 seconds. Now, judging from what was given, we can only use the second equation of linear motion, which is s is equal to ut plus a half at squared. We shall substitute the initial velocity, which is 40, substituting the time, which is 20, substituting the acceleration, which is a negative acceleration because the body was decelerating, it's a negative 3, and time it took to decelerate was 20. But remember, the formula has t squared, that's why we squared the time. When we simplify, we shall realize we shall obtain 800 minus 600. When we subtract, we shall obtain 200 meters as the distance covered by the body. Our last example involves calculating the final velocity of a body when you are given an acceleration of 2 meters per second squared and the distance that body covered was 5 meters. Now, judging from what we are given, we can only use the third equation of motion, which involves v squared is equal to u squared plus 2as. When you substitute in the formula, 4 represents initial velocity, s, which was 5 meters, representing distance covered, and 2 is this acceleration, which is a positive acceleration. That's why it is a positive, not a negative. Represents acceleration of a body, which is 2 meters per second squared. And we simplify. When you add 16 plus 20, you should be able to get 36. And you take roots both sides. Then you get your final velocity of the body as 6 meters per second. We have a simple exercise there. It involves 5 numbers. You can practice it and see how best you can improve. And in case you are challenged, you can send feedback via the email. Now, for more information, you can visit this link and find out more information involving linear motion and equations of motion. Wish you the best as you do the exercise. In case of any feedback, you reply on that website.